Every year, millions of people visit the Grand Canyon, and nearly all of them at some point stop at a water station to refill a bottle. Few of them ever think about where that water actually comes from, or what it had to travel through to get there. The real answer is stranger than almost anyone would guess. Nearly all of it starts as snow, falling on a high plateau miles away, before disappearing underground entirely and re-emerging days later through a hidden maze of caves that, until very recently, nobody had ever properly mapped. Scientists just spent months rafting, rappelling, and hiking through that maze to find out exactly how it works. And what they're discovering is reshaping how one of the most visited national parks on Earth protects its only real water supply. Almost the entire water supply for Grand Canyon National Park traces back to a single source, Roaring Springs, a powerful cave-fed spring on the canyon's north rim. You can actually hear it before you can see it from the North Kaibab Trail, though there's no direct path down to the spring itself. From there, that water gets pumped and piped throughout the canyon, supplying drinking stations used by hikers deep in the canyon's interior, as well as the broader ecosystem of plants and wildlife that depends on it throughout one of the driest, hottest landscapes in North America. Nearly all of that water begins as snow accumulating on the Kaibab Plateau, the high ground sitting above and around the canyon's north rim. When that snow melts, instead of simply running off across the surface the way water might in most other landscapes, it seeps directly into the ground and begins a complicated underground journey through multiple layers of rock before it ever reappears at the spring. For a long time, exactly what happened during that underground journey stayed almost entirely unknown. A real black box sitting beneath one of the most studied, most photographed landscapes on the planet. Researchers understood the water went in on one end, at sinkholes and fractures across the plateau's surface, and came out the other, at Roaring Springs and a handful of other springs scattered through the canyon. What happened in between the actual physical route the water took, the timing, the specific pathways through the rock, remain largely mysterious. Blasé Lasala, a doctoral student in eco-informatics at Northern Arizona University, working on this exact problem, has described the situation plainly, comparing it to staring at a black box, watching what goes in and what comes out, with almost no visibility into the process happening in between. That gap in understanding isn't just an academic curiosity. It carries real, practical consequences for how the park protects the water millions of visitors depend on every year. The rock beneath the Grand Canyon's surface is riddled with a specific kind of geological structure called a karst system, an extensive network of caves, fractures, and dissolved channels carved slowly through limestone by water over vast stretches of time. Researchers studying the system often describe it using a fairly vivid comparison. Swiss cheese, rock genuinely full of holes and connected channels rather than solid stone all the way through. Roaring Springs and other similar springs in the canyon emerge specifically from layers called the Redwall and Muav limestone formations, separated from the surface above by several additional layers of rock that water has to work its way through first. Here's the detail that makes this an urgent problem, rather than simply scientifically interesting. Dye tracer experiments conducted with the park's involvement revealed that water can move through this underground karst system remarkably fast. In some tests, dye poured into sinkholes on the plateau surface traveled roughly 20 kilometers underground and showed up at the springs in as little as 1 week. That speed might sound impressive on its own, but it creates a real practical vulnerability. Water moving that quickly through cracks and cave passages simply doesn't spend enough time in the ground to be naturally filtered the way slow-moving groundwater typically would be. If contamination, wildfire, runoff carrying ash and debris, or bacteria like E. coli enters the system anywhere on the plateau surface, it has a fast, largely unfiltered path straight down to the exact spring millions of visitors and the park's entire ecosystem depend on. In a scenario like that, park officials may have no real option beyond shutting down the water pumping system entirely until the contamination issue can be identified and resolved. A serious operational problem for a park that depends almost entirely on a single water source, serving an extremely high volume of annual visitors. If exploring a hidden world like this, one that exists directly beneath a landscape millions of people visit every year without ever suspecting it's there, is the kind of discovery that genuinely appeals to you, that's exactly the kind of science this channel is built around, so consider subscribing if you haven't already. Now here's how researchers actually went about mapping something this difficult to reach in the first place. To actually map this hidden system and understand where the greatest vulnerabilities sit, researchers had to physically go underground and document it firsthand, and the fieldwork involved was physically demanding. Research teams hiked as much as 2 full days each way just to reach some of the target caves, carrying roughly 55-pound packs loaded with specialized mobile lidar equipment. Once there, they hiked, rappelled, and floated through flooded passages on rafts to physically move through and document the caves, recording each passage's shape, dimensions, and the specific crack and fracture patterns visible in the surrounding rock. Using that mobile LiDAR technology, essentially a laser scanning system capable of building extremely detailed three-dimensional maps of a physical space, as researchers move through it, the team successfully mapped more than 10 kilometers of cave passages in just 45 days, producing the kind of high-resolution three-dimensional models of this cave system that simply didn't exist before this project began. Dr. Michael Sankey, another researcher involved in this project, has spoken candidly about how surprising the true scale of the find turned out to be, admitting he had no real sense beforehand of just how large and how long these cave systems genuinely extended underground. The resulting maps reveal specific fracture patterns and passage arrangements throughout the rock that offer concrete clues about how water actually moves through the system, information that simply didn't exist in any usable form before this mapping effort. Cave formation itself follows fairly specific, well-understood geological rules, and the particular patterns visible across a network of connected caves can reveal a real story about exactly how water has moved through the surrounding rock layers over time. Information researchers can now study directly rather than inferring indirectly from surface observations and dye tracing results alone. This research is also unfolding against an urgent real-world backdrop that underscores exactly why understanding the system matters right now rather than at some point in the abstract future. The Dragon Bravo fire has been actively burning on the Kaibab Plateau during the same period this research has continued, adding a real, active variable directly into the study, rather than remaining a purely theoretical contamination scenario researchers might discuss hypothetically. Researchers have described treating the fire as a genuine new factor to actively incorporate into their ongoing work, rather than simply an obstacle interrupting it, but its presence underscores just how quickly conditions across this specific watershed can shift, and how immediately relevant this mapping work actually is to protecting the park's water supply in something closer to real time. It helps to understand a bit more about karst systems generally, since that specific type of geology is the entire reason this hidden water network exists at all in a form this complex. Karst terrain forms specifically in landscapes built on soluble rock, most commonly limestone, the same rock hosting the Red Wall and Muav formations feeding roaring springs. Limestone is chemically vulnerable to slightly acidic water, and over sufficiently long timescales, rainwater and snowmelt gradually dissolve narrow cracks and fractures in that rock wider and wider, slowly carving out the caves, sinkholes, and underground channels that define a mature karst landscape. This process can take an extraordinarily long time to fully develop, sometimes unfolding across hundreds of thousands or even millions of years, layer by layer, drop by drop, gradually transforming what started as solid rock riddled with only microscopic fractures into the kind of extensively connected cave network researchers are now mapping directly. The Grand Canyon itself, carved by the Colorado River over roughly 5 to 6 million years, exposes multiple distinct rock layers along its walls, and the specific limestone layers hosting this cave system sit among the oldest, most heavily karst-developed rock, exposed anywhere within the canyon. This also helps explain why a sinkhole on the surface of the Kaibab Plateau can end up connected to a cave passage many kilometers away, sometimes with very little indication at the surface of exactly which sinkholes lead where underground. Karst systems don't develop as neat, predictable, evenly spaced networks the way a planned drainage system might. They form opportunistically, following whatever pre-existing weaknesses, joints, and fractures happen to already exist in the rock, meaning the resulting cave network can be genuinely irregular and difficult to predict from surface observations alone. That's precisely why dye tracing experiments, physically pouring a harmless, visible dye into a specific sinkhole and then watching for it to eventually emerge at a spring downstream, have remained such a valuable, almost irreplaceable research tool for this kind of system, since it's often simply not possible to predict which specific surface sinkhole connects to which underground pathway without directly testing it. The next phase of this research, beginning in early 2026, expands considerably beyond the cave mapping work completed so far. La Sala and Sankey plan to use airborne LiDAR surveys combined with decades of existing satellite observation data to map sinkholes across both the north and south rims of the canyon, while simultaneously analyzing patterns of snow accumulation and snowmelt stretching back roughly 40 years. Much of this next phase will focus specifically on surface features, rather than additional deep cave exploration, though researchers remain interested in investigating any newly discovered caves, if further opportunities arise during the course of the work. The core underlying goal is to build a comprehensive understanding of exactly how sinkholes, surface streams that disappear underground, and the broader underground water system are all connected to and influenced by the specific geology of this region, directly comparing surface-level patterns against what the team has already directly observed and mapped inside the caves themselves. Findings from this broader phase will also help guide and refine future dye tracing experiments, allowing researchers to test specific, informed hypotheses about water pathways, rather than tracing more speculatively across the plateau as earlier experiments largely had to. The practical stakes underlying all of this research are worth restating plainly, because they extend well beyond simple scientific curiosity about how an interesting cave system happens to function. Grand Canyon. National Park receives millions of visitors every single year, nearly all of whom depend directly on Roaring Springs for their drinking water at some point during a visit, whether refilling a bottle at a rimside station or filling a reservoir deep in the canyon's interior after a punishing hike in extreme heat. As the broader region continues experiencing hotter, drier conditions overall, the reliability and safety of that single water source becomes a genuinely serious concern rather than something that can simply be assumed to continue working exactly as it always has. Mapping precisely where water enters this underground system in the first place, and understanding roughly how quickly and along which specific pathways it travels once it does, gives park managers something they've never really had before: a real evidence-based ability to identify potential contamination risks before those risks actually reach the park's water supply and force an emergency shutdown affecting visitors already deep in the canyon. There's a broader lesson embedded in this research too, one that extends beyond the Grand Canyon's own specific water system. Karst landscapes, regions built on the same general kind of soluble, fractured limestone terrain, are genuinely common around the world, and they supply drinking water to a substantial share of the global population. By some estimates, roughly a quarter of humanity relies at least partly on karst aquifer systems for their water, the same basic vulnerability researchers are documenting beneath the Grand Canyon: fast-moving water through a fractured underground system with limited opportunity for natural filtration applies broadly to karst water systems, well beyond this one specific national park. Techniques being refined here, mobile, LiDAR, cave mapping combined with dye tracing and long-term surface pattern analysis, represent a useful, exportable methodology. Other regions managing their own karst-based water supplies could potentially apply to their own systems as well. It's worth understanding a bit more about the mobile LiDAR technology itself, since it's genuinely central to why this mapping project succeeded where earlier, less technically equipped efforts could not have. LiDAR works by rapidly firing pulses of laser light and precisely measuring how long each pulse takes to bounce back after striking a surface, building an extraordinarily detailed three-dimensional point cloud of the surrounding space in the process. Mobile LiDAR systems, small and light enough for researchers to physically carry through tight, irregular cave passages, represent a fairly recent technological development. Earlier cave mapping efforts typically relied on far slower, more manual surveying techniques, measuring tape, compass readings, and hand-sketched passage diagrams that could take dramatically longer to produce dramatically less precise results. Being able to walk, crawl, and float through a cave system while continuously capturing detailed three-dimensional data is part of why this specific research team was able to map more than 10 kilometers of previously undocumented passage in just 45 days, a pace that would have been essentially unachievable using older mapping methods. There's also a broader ecological dimension to this story worth understanding, beyond the direct human drinking water supply itself. The Grand Canyon's spring-fed water sources support strikingly unique desert ecosystems found almost nowhere else. Oases of vegetation and wildlife clustered around a handful of reliable water sources, scattered through an otherwise extremely arid landscape. Species ranging from native fish to migratory birds depend on these specific spring systems, meaning any meaningful disruption to Roaring Springs or the broader underground network feeding it carries consequences reaching well beyond the park's human visitors and infrastructure. Understanding precisely how this water system functions and what could realistically threaten it is directly relevant to protecting an entire web of desert life that has adapted specifically around the reliable, if previously poorly understood, presence of this exact water source for a very long time. So here's where this research actually leaves things. A water supply that millions of people rely on every year, casually, almost without a second thought, at a water fountain or a filling station, turns out to travel through one of the most poorly understood, genuinely hidden landscapes on the entire planet before it ever reaches a visitor's bottle. Researchers have now mapped more than 10 kilometers of that hidden cave network directly, revealing a fast-moving, genuinely vulnerable karst system capable of carrying both essential water and potential contamination with remarkably little natural filtering in between. The next phase of this work, expanding into decades of snowmelt and sinkhole data across both rims of the canyon, aims to finally turn that long-standing black box into something considerably closer to a fully understood, genuinely protectable system. We'll continue following this research as scientists complete the next phase of mapping across the Grand Canyon's water system. Thank you for watching, and I'll see you in the next one.